So I got my partner test back.
Uh-huh.
So just some of the problems that I missed.
Okay. So you're going to verbalize them?
Yeah.
Okay.
Okay. The first one I'm not really sure why I missed because I thought that I understood it, but I didn't get the right answer.
Okay.
So it's log base 2 of 2x plus log base 2 of x minus 2 equals 4.
All right. Let's do this from start.
Yeah.
By that I mean ignore what you did on the test.
Okay.
I want you to do this from the very beginning. So what's the first step?
Multiply 2x times x minus 2.
Yeah, the first step is to condense two log statements into one.
Yeah.
That's the first step. And what goes in the argument now?
2x times x minus 2.
Go ahead and multiply that out.
2x squared minus 4x.
Now, when you're trying to solve a log expression, convert it to exponential. So convert that. In other words, we have a single log expression. And once we convert it to exponential, you'll see it becomes a quadratic that we can solve.
Log base 2 to the power of 4?
No. When you convert it to exponential, you lose the log. Take the far left, raise to the power of that equals the argument. So what do you get?
2 to the power of 4. What is that? 32? No.
Well, yeah, but let's not worry about simplifying it until we get the whole thing written.
Equals 2x
Really,
squared.
yeah, I really think that I can't overemphasize that enough. That's 16. Because part of the problem is that when you try to do two steps in one, you make a mistake on one of them and then you get it all wrong. Now what can I do?
Subtract the 16 to the other side.
Okay, now what can I do?
You can solve the quadratic.
Let's try something before we do that.
Divide it all by 2?
Yeah, and I was going to say try factoring. It's always worth trying to factor it. And if you're going to factor it, the first thing you want to do is to factor out a 2.
Yeah.
Now you'll see that that does factor. And I can get rid of that 2 because I can divide both sides by 2.
Yeah.
So I got 0 equals what?
X okay, it's 4 and 2.
What are the signs? When I factor something, I separate the x squared term first. Then I determine both signs.
Positive or negative and negative?
Can't be. There's no way you can produce a negative 8. In other words, that sign right there tells you
has to be positive and negative.
Signs have to be different.
Yeah.
And now factors of 8 that subtract to the number 2.
4 and 2.
Okay, so what are my solutions?
X equals negative 2 and x equals 4.
Which of those solutions is extraneous because it violates the domain?
Negative 2.
So our only solution is that.
Okay.
Now,
yeah.
What did you do?
I had not done 2 to the power of 4.
Okay, that's the most important step is, well, and I'll say it both ways. If you're trying to solve a log equation, converting it to exponential is usually the step after you've reduced it to a single log expression.
Yeah.
If you're trying to solve an exponential equation, then almost always you're going to end up taking logs. So either type expression requires you to use the other. Always keep that in mind.
Okay.
What else?
Okay. Natural log of 3x to the 4th plus 6x squared minus natural log of 3x squared equals natural log of 50.
Now, do I need parentheses around these like that?
Yeah, parentheses is around all of the arguments.
Okay. So, next step.
Divide.
No. Well, when I say next step, are you going to condense these two log expressions? We got one there and another one there, and they're being subtracted. So you know right off the get-go, you can condense that into a single log expression.
Yeah.
That's going to be valuable here, because then I'll have the log of something equals the log of something else, and I'll just be able to set the arguments equal to one another. So what does this one become?
3x to the power of 4 plus 6x squared divided by 3x squared.
Equals
natural log of 50.
Okay. And you can go ahead and do this. What do you get when you simplify that argument?
Natural log of well, wait, you can't set them equal to each other?
Well, you can, but you can simplify this first argument fairly easily. Divide top and bottom by 3x squared.
So x squared plus 2 equals natural log of 50.
And now, what's the next line?
Now you can set x squared plus 2 equal to 50.
Yeah, this is the one time that you don't have to go through conversion to exponential. Is when you end up with natural log on both sides, or log-based something on both sides, then you can set the arguments equal to one another, and you don't have to convert it. So if x squared equals 48, does x equal to?
Plus or minus the square root of 48.
Simplify that. They're always going to want you to simplify a radical if you can.
48 is 8.
What you're looking for is the largest factor of 48 that is a perfect square number. Consider, and the way to do that exercise is to look at your perfect square numbers. Now, what's the largest one of those that's a factor of 48?
Is 16?
16 is actually it. Hard to see, but so it's 16 times 3, so it's 4 root 3.
Yeah.
Now, you would actually get there if you used 4. It would just take 2 more steps.
Yeah.
So you can always simplify radicals by finding any perfect square factor. But if you want to do it the quickest possible way, find the largest one.
Okay.
Now, do either of those solutions, in other words, this solution and this solution, do either of them violate the domain? And when I say that, I mean this, well,
I don't think they
I
do.
mean this. That's the first domain. That's the second domain. And
No.
you're correct, they don't. The negative's not going to hurt at all because we're taking it to the fourth power, which is going to turn it positive, and we're squaring it, which is going to turn it positive, and we're squaring it, which is going to turn it positive. Now,
Yeah.
one cautionary note.
Yeah.
That and this are not exactly the same. We pretend that they are
Okay.
because they are exactly, in other words, dividing the two arguments, giving you x squared plus 2.
Yeah.
The reason they're not exactly the same is because when you go to check out your answer, it makes a great deal of difference sometimes whether you check it out in the original or in that one. Sometimes it will violate the domain in the original and will not violate it in the simplified.
Oh.
Yeah, strange, because you would think that they're exactly the same, but they are not in terms of domain violations. So the secret is you always have to check your domain in the original problem that was given to you. Not
Okay.
in secondary steps or third steps or anything like that. In this particular case, it doesn't matter. It does not violate the domain either in the top row or the second row. But most problems, it does matter. And if you go to the second row, you won't find any domain violations, but if you go to the original problem, you will.
Yeah.
Be careful about it.
Okay. Natural log of, and this is all in parentheses, x cubed y divided by w z to the power of -2, and all of that in parentheses is squared.
Okay? And you're just supposed to expand this.
Yeah.
Okay? It's the first step.
Bring the negative, or put the z on the top.
That would probably be my first step also. I like that. For one thing, it eliminates all negative anything.
Yeah.
Second step.
I would square each term,
Yep,
maybe?
I like that also, as opposed to bringing the 2 down there first.
Yeah.
If you bring the 2 down there first, it can confuse the issue.
Yeah.
Because then you don't know whether that 2 goes as an exponent to each term or not. But if I go ahead and square everything, then what do I have?
X to the power of 6, y squared, z to the power of 4 over w squared.
Now separate it.
So do you have to put natural log in front of everyone?
Uh-huh. In other words, yeah, go ahead. You'll see.
So natural log, or is it 6 natural?
Well, it depends on whether you want to do it in one step or two.
Okay,
I would go ahead and do it in 2 steps. I mean, 1 step.
Okay, so plus 2 natural log of y plus 4 natural log of z minus double natural log of w.
What happened to my 2? I need a 2 there, don't I?
Oh, yeah.
Yeah. So it's
Minus
2 natural log of w.
w.
Yeah. And then there's no question. In other words, once you square everything first, it's much easier to convert that or expand that than it is trying to expand it and trying to figure out what you would do with that 2 if it were down there.
Yeah.
And in fact, had they given you this as the problem, my first step would be to take that 2 up to an exponent and go ahead and square everything.
Yeah.
Because then you are never in doubt when you get to your final answer.
Okay.
The other way can leave some doubt. Okay.
Okay. The next one is 2 log of 3.
Okay.
There's no base, so I'm assuming it's
10.
next.
Common log.
Minus 3 log of x plus log of z plus log of y.
Plus log of what?
Y.
What's the third one?
Third of one is log of z.
Z. Plus log of y. Okay.
Yeah.
And this is just an expression they want you to condense?
Yeah, they want you to,
Okay.
yeah, condense it.
So give me the next step. Let's do it one at a time this time.
Maybe square it, so log of 9.
Yeah.
Minus log of x cubed plus log of z plus log of y.
And now it's really easy to condense all into one log expression.
9, wait.
Because I see addition and subtraction going on, I know our answer is going to have a fraction in it. Well,
Yeah.
so I go ahead and draw that fraction bar in there. Now, what goes in the numerator? 9 for sure. What else?
Z and y.
What goes in the denominator?
X cubed.
Yeah. And again, it's helpful if you do this first.
Yeah.
In other words, handle that coefficient first. Then once there's no coefficients on anything, it's pretty easy after that.
Okay. So we're also doing like recursive and like exponential like formulas and stuff.
Arithmetic series and geometric series?
Yeah.
Okay. Let's do some of those if you'd like.
There's a problem. Should I read the entire thing? It's like a
Go ahead.
It's like a story problem. Okay, so the International Villain Bank offers continuous compounded interest rates.
Okay.
You being a master villain, only deposit $1,000 into an account, and 5 years later you have $201,170. Determine the interest rate you used by graphing.
Okay. What is the general formula for continuous compounding? There actually are 3 different formulas for compounding.
Well, the one he used in the answer
go ahead.
was A equals PE to the power of RE, or RT.
Right. The other one is this one. That is for annual compounding.
Yeah.
And the middle one is A equals A sub 0 times 1 plus R over K times KT, where K is how many times a year it's compounded.
Yeah. But if it's continuous, then wouldn't it have to be the last one?
Correct. And
Okay.
notice that continuous means K is infinite, right?
Yeah.
Let's say, in other words, annual compounding is once a year. If you find a bank that compounds once a month, then K
Yeah.
is 12. If you find a bank that compounds once a week, then K is 52. If
Yeah.
you're talking about continuous compounding, which is the only real thing in nature, in other words, nature does not offer anything that's annual compounding or compounding on a monthly basis. If you look at the bacterial growth in a petri dish, it's always continuous compounding.
Yeah.
If you look at populations multiplying, whether it's rabbits or anything else, it's continuous compounding. Okay? So
Yeah.
continuous compounding is the most important one. But we as humans have banks that actually started out annual compounding on pretty much everybody. They invented this thing called annual compounding. So these first two formulas apply there. But in your problem, they said continuous compounding. Okay? So I'm going to use this formula. And they said do it by graphing, but that's the general formula. What is the specific one for this case?
Like with the numbers plugged in?
Yeah, and then we'll do it by graphing if you want. Although I prefer to do it by using logs, but go ahead. But put the numbers in.
201,170 equal, or wait, actually, I don't know if that's A or if that's P.
It's the same thing. P is the same as A sub 0. In other words, P is your starting amount. A sub 0 is your starting amount. So is it up here.
So 1,000
Uh-huh.
is, um,
E is a number.
E to the power of R times 5?
Exactly. Now, if I were going to try to solve that algebraically, which I think we can do easier than solving it out graphically.
Yeah.
Well, first of all, let's cover how to solve it graphically. What kind of
Would you,
calculator do you have?
TI Inspire
Okay.
CX Cap.
Okay. How do you solve this
I
graphically?
think plug in each side for Y and then see where they intersect.
You got it. Okay. So that's easy enough to do. So you
Yeah.
don't need my help doing it.
So would you
Let's
just
solve
like,
it. Let's solve it algebraically or using logs. And the reason I say we're going to use logs is because what we're solving for is R. And R is in the exponent. Whenever you see your variable in the exponent, know that you're going to have to use logs.
yeah,
Okay? So what's the first step I'm going to take in solving this thing?
I would divide 201,170 by 1,000.
What's the next step?
Um, Make the log function?
Take the natural log of both sides. Notice
Okay.
what happens. In other words, I'm looking at an exponential function. What I was saying is that when you're trying to solve an exponential function, you're going to have to use logs. And the perfect log to use is the natural log, because our base over here is e. So if I take the natural log of the left side, I got to take the natural log of the right side. That
Yeah.
is just a number. What is this? The natural log of e to the 5r power.
Uh, 2.71 times e.
It's 5r. In other words, first of all, I can move that 5r down in front, right?
Okay.
And the natural log of e, well, that base is e. So e to what power is equal to e? 1. Whenever
Yeah.
you take the natural log, or excuse me, whenever you take the log base of b, it's always 1. If I say the natural log, or excuse me, if I say the log base 17 of 17, that's equal to 1. It doesn't
Yeah.
matter. The log base b of b is always equal to 1. Well, in this case, we have log base e of e. So now I have 5r equals this number. So r equals natural log of 201.17 divided by 5. Now, that's not the same as natural log of that numerator divided by natural log of 5. This is just 5 in the denominator.
So you can't simplify it more?
Oh, you can. Well, that's the exact answer.
Yeah. Well, my teacher said that we're not supposed to plug in 2.71 for natural log.
You're not. Just
No.
like you never plug in 3.14 for pi anymore either.
Yeah.
Natural log functions tend to almost always be irrational. So it's very rare that a log function will reduce to a whole number. If it does, fine. This reduces to 1.
Yeah.
But if it reduces to anything but a whole number, it's going to be irrational, and you're going to be rounding off if you use the number. So this is the proper answer. Natural log of 201.17 divided by 5. Now, if you want to know what that rate is, let's find it out, because notice that he's run $1,000 up to $200,000. Not in any bank that I know of.
Yeah.
And that's why they said the crooked guy. So
Yeah.
do you have your calculator?
Yeah, I'll grab it real fast.
Okay.
Okay, I got it.
Do the natural log of 201.17. Take that answer, divide it by 5.
Okay.
And we will round it off just for the sake of what kind of interest rate is this guy getting? Must be like 200% a year. More than that, even.
I got 1.06 for R.
What'd you get when you took the natural log of 201.17?
5.304.
Oh, 1.06. Yeah. That means he's
It
getting
was a
106% interest per year.
yeah.
Nobody pays that.
No.
Right now, banks are paying like 3%. So R would normally come out to look like something like this. When it comes out to that's first of all an outrageous number. Maybe if you're buying Bitcoin or something, you'd find R's that were on the order of that level. But
Yeah.
for non-risky bank type stuff, the rates are always going to be between 1 and 10%. My entire lifetime, they've been between like 1 and 12% max.
Okay.
They do vary, but this guy somehow must have hacked into the bank system and got him to pay him, instead of 6% interest, 106% interest.
Yeah.
Now, even at 100% interest per year, that just means your money's doubling, right?
Yeah.
So the end of first year, you'd have 2,000. Into the second year, you'd have 4,000. Into the third year, you'd have 8,000. Into the fourth year, you'd have 16,000. Into the fifth year, you'd have 32,000. So what do we have going on here? That doesn't make any sense.
I don't know.
Yeah, I don't either. Let me think about this for a second.
Although the right answer is 106%. That's
Yeah, I just don't get it if you work back through it. Now, there's an extra 6% that I didn't take into account when I was doubling these. But if R was 1.00, then you'd be doubling your money every year.
yeah.
But doubling your money every year doesn't get you anywhere close to 201,000. It only gets you to 32,000. It's hard for me to believe that that extra 6% makes that big a difference.
Yeah, I don't either think so.
Yeah.
No.
Huh. But that's okay. We won't waste our time trying to figure out why that. I do trust the math. It's not your teacher I'm doubting. It's the math of the thing. But I can't see where we made any mistakes. So, now, when you did the natural log of 201.17,
Yeah.
let me see if I can do that real quick. Oh, goodness. It's been so long since I've used this. I have an Inspire also. Where's the natural log cube? Oh, I see it. It's the blue. And 201.17. Enter. Yeah, I get the same thing. 5.304.
Yeah.
Interesting. All right. Well, strange, but
Yeah.
I can't think of any part of that we didn't do correctly. Huh. All right. Well, I might have to think about that, and if I discover a flaw in our logic, I'll let you know next time.
Well, don't you have to multiply it by 1,000 because that's what you started out with?
Well, you start out with 1,000. At the end of the first year, if you make 106%, what do you got?
Like roughly 2,000. Yeah.
2,060. And now you're going to make 106% on that. So it's going to go to, I don't know, something like that maybe. And
Yeah.
that's the start. That's at the end of 1 year, 2 years, 3 years. Let's say it goes to 9,000. 4 years, 20,000. 5 years, 40,000. I don't get it. We're still off by a factor of 8.
Yeah.
6. About 6.
I'm not sure how that is.
Yeah, even if we went 6 years, I'm not sure what's going on here. I got to think about this a little bit.
Yeah.
Because surely that's what an R of 1.06 means, is 106% is your rate of interest. And I don't know. Let's go on rather than wasting more time on it. I'd say
Okay.
we did it correctly, but
Okay, so there's another one, and it's worded, it's very wordy.
okay.
So I think it's kind of tripping me up.
Okay.
So suppose you buy a 7-year-old car used, or a 7-year-old used car that costs $5,000.
Okay.
3 years later, the car has a value of $3,500.
Okay.
You do some research on this particular car and discover that the value of the car will never drop below $2,000. Assume the value of the car varies exponentially with the age of the car.
Okay. What do they want? The rate of depreciation?
They want you to come up with an equation,
Okay.
an exponential equation.
When you're dealing with anything that is depreciating,
Yeah.
it's continuous. Nobody
Okay.
has really come up with the 1 year and the 1 month and the 1 day depreciation rates. In nature, things depreciate on a continuous basis. So you use the same formula.
Really?
Huh?
The answer was AB to the power of X plus 2,000.
Well, let's start it. In other words, we're going to use the same general formula.
Okay.
Okay. And the fact that it was 7 years old when we bought it can't matter because they didn't give us the original price.
Yeah.
So that information is irrelevant unless they give us an original price, in which case we would be able to calculate the depreciation in that 7 years.
Yeah.
But they didn't give us. So we're going to treat it like it's a brand new car, $5,000.
Okay.
Okay. So what we know is that it's now worth $3,500. It's the current amount.
Yeah.
The original amount was 5,000.
Yeah.
And this time it's R is negative
Okay.
as it's depreciating. So you can do this a couple of ways. You can leave it as RT and calculate that R is negative. Let's do it that way. That's not typically the way math handles it. Math sticks a negative sign in front of that, and sometimes they'll say that. Have you seen that?
Uh, no.
Well, let's talk about it. We don't need to do it that way. I can't quite figure out why math does that. We're going to do this, and we're going to calculate an R that's negative. What's first
Okay.
step?
Wait.
And I'm not quite sure what to do about that, but we'll talk about that after we figure out. And what is their question exactly?
It doesn't say that, it doesn't have a question, but it has like a y equals where we're just supposed to write the equation.
Okay. We're almost done writing the equation. The only thing we're missing is R.
Okay.
So if we can solve for R, we'll fill it in, and then we have, in other words, this is the general equation. And
Yeah.
when we only have one variable left, t, we're going to have the specific equation.
Okay.
Okay. First step,
Divide 3,500 by 5,000?
get that.
Yeah.
Right?
Yeah. Natural log of,
Hold on a second here. Excuse me, I didn't write this correctly. 3 is t. It's 3r.
Okay.
Right? In other words, is all I did was fill in the 3 years, fill in 3 for t.
Yeah.
Now, let's solve for r.
Do we find the natural, or take the natural log of it?
Yeah. And believe it or not, you should always use natural log, regardless of whether you're dealing with e or not.
Yeah.
Particularly convenient when you're dealing with e. Saves you a step. But even if you're dealing with numbers like 5 instead of e, I would still take the natural log of both sides.
Okay.
Okay? And just trust me for now that you can never go wrong by just always taking the natural log of both sides.
Okay.
Okay? So what's the next line?
I know that the E changes.
Hold on, let's do this one step at a time. What are we going to do over here?
You can bring the 3R to the front.
Yeah, or just understand that when you take the log base b of b to the x power, the answer is x.
So 3R.
It's always going to be 3r if it's over natural log of e. Because
Okay.
yeah, it's 3r times natural log of e, but that's always 1.
Okay.
Now we still have this over on the left side. We're going to divide that by 3 to solve for r. And let me point out one thing.
Yeah.
When you take the logs of numbers between 0 and 1, they are negative answers. Notice what the log chart looks like. The log graph looks just like that, with that being 1 comma 0. So every time you take the log of a number that's between 0 and 1, the answer is down here, negative.
Okay.
So that's going to be negative. We're dividing by a positive, so we are going to get a negative r. What's your calculator say it is?
Let me do that real fast.
And you can put in natural log of 0.7.
Okay.
Makes it a little easier, I think. You don't have to use parentheses or anything. And then take that answer first and then divide by 3.
So I got negative 0.1189. Yeah.
So now what is our specific equation, which is what they wanted to begin with?
3,500 equals 5,000.
Actually, to get the specific equation, we're going to leave that as A. We're going to leave that as P. We're going to leave that as E. But this is going to become minus 0.1189 T. And now that will cover all situations. In other words, if you're having this kind of depreciation, which is about what, 12% a year?
Yeah.
It's probably correct, realistic in today's car market, about 12% a year. In other words, if you buy a car and leave it in your garage, it's going to be worth 12% less 1 year later.
Yeah.
Even if you don't drive it. Okay? But this can be used probably for any car that is this make and model and approximate price range. That's why this is the specific. I suppose you could say just for this particular car, then A is going to be 5,000 times e to the minus 0.1189 t. So that car will always be worth that based on however many years you hold it.
Because the next question is predicting the price when it is 13 years old. So you just plug in 13 for T?
Exactly. And
Okay.
then that you can get out of your calculator.
Yeah.
Hold on a second. No. The car, that's why they told us it was 7 years old to begin with. So, since we assumed it was new at 5,000, then when they say, what's it going to be worth at, what, 13 years?
When it's 13 years old.
Well, that makes T6. In other words, that's 6 years after you bought it, correct?
Yeah.
Okay. So T is 6. And the reason they gave us that last piece of information is that it'll always be worth a minimum of 2,000 is in case this number comes out to be less than 2,000 when you put in 6 for T.
Should I plug it in?
Sure.
Okay.
Then the answer would be 2,000. If this comes out to be 1,900, then the answer is 2,000.
Oh.
Right?
Yeah.
If this comes out to be $250, then the answer is 2,000.
Yeah.
Well, 6 times that, that's going to be a pretty big R. That's what? E to the minus 0.7? What is that? Or when you plug in 6 for T, what do you... I usually do that first in my calculator, and then I multiply it by 5,000.
I got negative 0.71.
No, never going to be negative.
For the exponent. Just the exponent.
Okay, but notice that negative exponents do not make for negative numbers. Now take e to that negative exponent.
Okay. 0.49.
Multiply that by 5,000.
Oh, wait. Whoops. 2,450.
2,450. That's what the car's worth.
Okay. That makes sense.
Yeah.
And then the next question is, what is the original value of the car when it was new?
Aha. Based on the same depreciation rate.
Yeah, I think so.
Okay. Well, we've got an R, our depreciation rate. I'm going to write it up here in a different color. We've solved for R for this car. Now, what formula can we write to figure out what its original new price was? In other words, that's what it wants, right? What was the car priced at when it was new?
Yeah.
Okay.
You don't use the same formula?
Well, you do. But everything's a little different. In other words, what's this amount going to be?
I don't know.
5,000. P is what we're trying to solve for.
Okay.
P might be 10,000, right?
Yeah.
Because it's worth 5,000 after 7 years.
Yeah.
So whatever P is what we're solving for. We know R. I'm just going to round this off. And we know what T is, 7.
Yeah.
Only one variable in that equation, and that's that one right there.
Okay.
So that is going to be 5,000, and this is an algebraic equation, divided by e to the minus 0.84. Go ahead and come up with that number on your calculator.
Yeah.
We'll see if it makes sense.
11,492.
And that does make sense. In
Yeah.
other words, in 7 years, it lost a little bit more than half its value. And we know that 6 years later, lost a little bit more than half its value. And 3 years later, it lost about a third of its value. So everything is in the right ballpark.
Okay.
But this is always the equation you're going to use. It's just sometimes that 5,000 is the new price, sometimes it's the A. In other words, in the first case it was P, but in the second case it was A, to figure out what the original new car price was based on this depreciation rate.
Yeah.
And that's assuming that that depreciation rate stays the same year to year, which is not necessarily a realistic assumption, but it's close.
Yeah.
Probably is more dynamic. In other words, it wouldn't surprise me if new cars depreciate at maybe 20% the first year. They say when you take a new car off the lot, you've lost 10% immediately.
Yeah.
So it doesn't have to depreciate at the same rate every single year. But this problem kind of depends on it doing that.
Yeah.
But in real life, it might not. It could be dynamic, more so than this problem suggests. But it's probably close.
Yeah.
All right. We got about 10 minutes.
Okay.
5 minutes, sorry. You know what? I'm always looking at the wrong clock. Let me look. Yeah, we got 5 minutes. Okay.
Okay, let me look for another problem.
So you're not into arithmetic series yet, or geometric series?
We are. That was the last problem.
Okay, that was logs and exponentials go together. Okay, all of those problems regarding money put into banks and earning interest, or something decaying or depreciating, that's exponential. That goes with logs. Logs and exponentials go together like steak and potatoes. Okay?
Yeah.
Arithmetic sums and geometric sums are a whole nother subject. So if you want to touch on those, we can do so.
Yeah, it's like a shifted geometric.
Like a what?
A shifted geometric sequence.
Okay.
So it's 1,930, 867, 810.3, 759.27.
Hold on. 810.3, and what's the fourth term?
759.27.
All right. Now, I'm not quite sure what you mean by a shifted geometric series.
It's where you have to subtract and then divide to find the common ratio. So first you have to like subtract
from everything? From all the numbers?
Like you subtract the second from the first.
Right. In other words, the normal way of solving for the common ratio would be to just divide the second term by the first term.
Yeah,
Now,
but here you have to
common ratio. But clearly they're not the same here, because if we divide the third term by the second term, we don't get that same ratio.
Wait, the first term is 1,000 and then the second term is 930.
Ah. Now, that might work. So the question is, that is 0.93, looks to be the common ratio, but is 867 divided by 930, what's that equal to?
Wait, 867.
Yeah, if this were just a normal geometric series, these ratios are all going to be the same.
0.93.
Okay. So I'm not sure why he called it a shifted one.
Well, because if you subtract and then divide,
Uh-huh.
then you get a common ratio of 0.9. So if you were to do 1,000 minus 930 and get 70, and 930 minus 867 and get 63,
Okay.
and then you divide those, divided by 70.
This one's like 57.
Yes.
And I see what you're talking about.
And then you divide those, and then you get 0.9 for all of them. But just 0.9, not 0.9.
Yeah, well, I'm a little confused. Because if I look at the explicit formula for a geometric series,
Yeah.
it's the first term times common ratio to the n minus 1.
Yeah.
And I don't need to look at the 70, 63, and 57. I can see that that's going to give you something. I'm just not sure why we're looking at it. In other words, is this a true statement? In other words, I know what the first term is, 1,000. I know what the fifth term is. So I can prove, is this correct? And I can solve for R.
I'll see.
And R is going to be 0.93.
Huh.
Yeah, your teacher is talking about something that I'm not sure what he's talking about. But that's okay. When you take honors, that frequently happens, is that they'll go way beyond Common Core.
Yeah.
They'll get into subjects that nobody else has ever presented to me since I've been tutoring.
Yeah.
But this is as long as the ratio of the second term divided by the first term is the same as the ratio of the third term divided by the second term, which is the same as the fourth term divided by the third term, and in this case they all appear to be 0.93. So R is definitely 0.93. And if I put that in there, you can prove it. Take 0.93 to the fourth power.
Then we'll. Oh, it's because it has like a shift at the end. So it should be like, because it's recursive, should be u of n equals u of n minus 1 times 0.9, and then it has minus a value.
Oh, okay. All right, let's back up a little bit.
So.
Hold on a second. Yeah. So first of all, this is the explicit. That'll give you any geometric series where you know the first term and you know the common multiplier.
Yeah.
When you look at the recursive formulas are always based on the preceding term.
Yeah.
So a sub n is always going to be r times a sub n minus 1. That is the recursive formula for a geometric series.
Yeah.
Now what you're telling me is that there's some constant being subtracted from that.
Yeah.
And you're saying R is 0.9?
Yeah. Because that's when you get when you subtract and then divide. and then the number you subtract at the end is 30.
So this is always 30?
Not always, just in this
In
scenario.
this problem.
Yeah.
So let's test it. So a sub 2 should be equal, and you're saying r is 0.9. Well, we'll solve for r.
Okay.
And it's based on 1,000 minus 30, right?
Yeah, I think so.
We know a sub 2 is 930.
Yeah.
So now if I add 30 to both sides, I get 960 equals r times 1,000 divide, I get an r of 0.96 instead of 0.93.
What?
Yeah, I know. So
I don't know.
More puzzle. Yeah. It actually would work if we were adding instead of subtracting. If we were adding 30, because now I'm going to subtract 30 from both sides, making that 900, and then r comes out to be 0.90. So
Maybe that's what he meant.
if they gave you that recursive formula, and they gave you those 5 numbers in the sequence, then r would be 0.9.
Yeah. So we were supposed to come up with the sequence ourselves. The only thing that we were given were those 5 numbers.
Well, I don't understand. Oh, you got to come up with the recursive sequence.
Yeah.
Well, I don't get it, because if I'm going to come up with the sequence, the first one I'm going to come up with is the explicit, and the explicit is equal to this. The second term is 930. It's equal to the first term times r to the 1. If I solve that for r, I get 0.93. And that works for those 5. Now, if I try to come up with the the recursive, then a sub n is going to be 0.93 times a sub n minus 1. There's my recursive formula. I've never dealt with geometric sequences where they shift it like this. So I'm not quite sure what I'm doing here. But I don't understand why this isn't the answer. What?
I think I do understand it for the most part.
Okay, good. It's not necessary that I understand it as long as you understand.
Yeah, I think.
All right. Zoe, I apologize for taking you over. I'll let you go.
Thank you.
Have a good day, and I'll talk to you next time.
Okay, thank you.
You're welcome. Bye-bye.